Okay, factoid number one. A moving charged particle creates a magnetic field. A moving charged particle. Nope. A moving charged particle creates a magnetic field. Okay. Obeys the right hand rule. Okay. So as it goes through space, this craziness creates a magnetic field. As it gets closer, it gets stronger. As it goes as it's further away from it, it's weaker. Okay. So the Biot-Savaar Law, yeah, it's like it's strong. It's stronger here, closer, and gets weaker as you go further away, radially away. It's stronger here than it is over here. Okay. So it's a cross product. So we're looking for the component that is perpendicular. So here we're looking at the velocity and the component that is perpendicular. So looking at that angle, right, orientate our axis like that. We're looking for this component here. Actually, sorry. This is the radius vector. We're looking for that component there. Okay. Well, sorry, no. We're looking for the unit vector's perpendicular component. Okay. So that's where this sine theta comes from, finding this opposite side here of this angle. Okay. So it is orthogonal to both of these. This is why we have to use the right-hand rule. Or when we do a cross product, we always get a vector that's going orthogonal to this plane of the vectors, perpendicular to that plane. Good with that? I would just tend to do this and just do the right-hand rule to figure out the direction. Okay. This is not given on the equation sheet. Pretty sure. Yeah. But this is kind of like foundational. That's kind of where it starts. Okay. So the unit for magnetic fields is Tesla. We're going to be using the permeability constant, 4 times 10 to the negative 7th Tesla per meter, Tesla meter per amp. Okay. This is different than the permittivity constant, epsilon naught, so mu naught. We use this for charges, and we're using this for magnetic fields, like this electric field stuff, magnetic field stuff. Okay. So here's another animation to show this. that. Gets maximum there. Okay. Charged particles going into the screen. The correct answer is up. Good with that. Right hand rule. Technically, if it was a negative charge, you'd use your left hand. Okay. But you don't have to worry about that. Just giving you full disclosure. Have a conversation.
Oh, yeah.
Yeah, that's true. Hey, see me do the same answer.
Technically, D implies C.
C actually implies, D doesn't imply C. But C includes D. Because if you say C, the answer is D. So I'm going to stick with C then.
I wouldn't be. Sin, that's fine.
I don't see how that's.
Yeah, but it's gotta be zero.
Is perpendicular to all other vectors. It's just violating.
Do what?
For zero vector orthogonal to all vectors in the R3 space.
Correct answer is D. Okay. Here's the radius vector. There's no component of velocity that is perpendicular to that radius vector. You okay with that? Okay. Tell your neighbor.
Yeah, but they're all just like the induced field, but they also have choices.
But it's asking specifically about the magnetic force.
Oh, okay.
He's not well, yeah, specifically perpendicular. Yeah.
So we're considering
It's not A or B because it doesn't get closer or farther away. It just
No, we're just considering the magnetic force. It says the magnetic force.
yeah, the magnetic force could be from a point charge 45 feet. Wait.
That's the direction of magnetic field. Magnetic
Because
field.
we're still up to this.
right. Exactly. Force and
It's just like the wire.
Correct answer is A. This. Some of you made this connection. I heard you. The question we did yesterday with the two wires with current going this way is the same concept. Same thought process. Same. Does that make sense?
Would the, I guess it would be dependent on the velocity, but would there be a case where the magnetic field and the electric field cancel out and they just continue straight?
Hmm. Yep. Special case, but yeah. Okay. Sorry, Josiah.
So, if the magnetic forces are attractive and repelling, why do we represent the field as like a big circle rotating around it if the forces just... Why do we have the force perpendicular to the field? I understand like how it works mathematically. I'm just questioning why would anyone ever design it like that? That doesn't answer.
It's a good
The
question.
question isn't how it works,
Are you
it's
saying
why
why
does it...
Why
is the systems we use to understand it designed like they are?
I don't know.
How it works.
Josiah, it's a valid question. I don't know the answer to that.
You don't know the answer?
I have no idea.
Thanks.
I've never really questioned it. I was like, man, that's messed up. I don't know. Moving on. Because, okay, maybe, Josiah, maybe this. I've got a hypothesis because we studied magnets, like bar magnets, permanent magnets, prior to understanding where they came from. So when you do iron filings on a bar magnet, you get the magnetic field. How's that?
Okay, so just because we study things in the... So same reason why current is backwards, got it. We study things in the...
Okay, so this is getting more, so this was like foundational stuff. The AP starts here foundationally. We're looking at current in wires, small amounts of charge going through, okay? So you've got a certain, you have like a drift velocity and those based upon Ben Franklin positive charge carriers, that's like the pretend thing that's flowing through the Ben Franklin thought that we just have stuck with, moves a certain distance. Okay. So that speed can be represented as distance over time. We can measure the distance, and so this, we move the delta t over here, and that becomes current. Okay. And so, we can look at it like this. So here's how it's written on the equation sheet. Okay. So they use delta L instead of delta S. And what you're looking at, actually, I'm going to do a little different here. I'm going to orientate my axis parallel to the radius. Okay. So I'm going to look at the component of current that is perpendicular to that radius vector. Okay. So I want this part here that is perpendicular. So you could write it like this. Okay, with that, Jared.
So on the AP equation sheet formula,
Yep.
what is that R? Is that like the R from the point to the field, or is that?
Yeah. The point of the wire compared to where you're trying to observe. So this distance here. And then this is just the unit vector of that, which I don't expect anybody to use this equation in that form. Either memorize it like this or like that, and recognize you need to tilt the axis in line with the radius. Okay, so that's where the AP test starts, as like here's foundation. It's kind of like here's Coulomb's law. Okay. Good with that? Is everybody good with out of the page? Okay, right hand rule. Right there. Yep, you may. Tell your neighbor. I go C. Good with that? have a conversation.
Oh, I didn't see the balance.
Okay, everybody good with what the correct answer is? What do you say? 1. Good with that? Because you got a r squared here. That's x squared plus capital R squared. Take the square root of that, but then square it, so that gets rid of the square root. And then you got another one over here. So there's your 3 halves. And you're going from infinity to negative infinity to positive infinity. Okay? I'm not going to show you how to do that.
Why is that a negative x? Yeah, that's impressive.
I have no idea.
This is a question that is gripping me as I.
Oh, because they made this point the origin. You can't see me.
Why would they do that?
I don't know.
Why would they sign them? Why not?
Just mess with you.
I would find out this last.
I don't think it doesn't change anything because you're going from infinity to negative infinity. All right. So this is like doing calculus with Coulomb's law. We got Ampere's law coming up. That's going to make this calculation super duper easy. Okay. So after we do some crazy calculus, we'd end up with this equation, which is going to be what Ampere's law is going to show us. Okay. Jared.
So about those 3 main formulas for the long and wire, the loop, and solenoid.
Yeah.
Worth memorizing the field formula for those 3.
Sure. If that's an easy ask, yes. Yeah. Yes. Yes. We're looking in versus out, not clockwise versus counterclockwise. Tell your neighbor.
That's true. I know.
Correct answer is correct answer is B. Beautiful barnacles. Bodacious barnacles. All right. Get to that because it's just R. It's over R. Okay. This is the shape. Just like with charges, you had to do Coulomb's law with calculus with the ring for electric field. You got to do this with, you got to do calculus with this. But there's some simpler things, okay? So here, if we made this our axis, how much of that current is going perpendicular to this radius vector at the center? All of it. You okay with that? Okay. So this just goes to 1. You all right with that? Okay. So you got mu naught over 4 pi is equal to I over r squared. Nope. Because the r never changes as you integrate from, so this is dl, as you integrate from 0 to 2 pi r. You all right with that? So we're pulling all this stuff out because it's constant. Super duper nice. And then when we integrate dl, we just get 2 pi r minus 0. So pi r, and one of those 2's goes out, leaving us with mu naught times the current over 2r. That one's worth memorizing. This is the magnetic field of a ring loop. Okay. And you could throw in there n for number of loops or turns. Good with that? Okay. Oh, look at that. So this follows, you do the alternative right-hand rule to figure this out. And this lends us to, hold on a second, let me see if I talk about magnetic moment. And this is where magnetic moment, so this, I don't know why they keep doing, did they use this for the magnetic moment in this book? Yeah. So this is just a a tool, sort of a shortcut that they use. So this would be the area on the current, and it's always perpendicular. It's going in the direction your thumb's pointing. Okay, it points towards the North Pole. You all right with that? Magnetic moment. Tell your neighbor.
Oh, it says mu Noah want I over H.
Correct answer is A. Okay, there is no component of current that is perpendicular to the radius. It's going parallel. Okay. Good with that?
Sure.
Have a conversation. There we go. D into the page. Tell your neighbor.
What they do. It's have two fields.
Okay, is everybody good with A? This one's closer. Has a stronger magnetic field than this one coming out of the page. They're in opposition. Okay. So, what is the magnetic field at point P? This scenario, this magnitude of it. So we're going from, for half the arc, you're going from 0 to pi r for half of this. And then you'd subtract the other half, like with a different radius. Good with that? Okay. James. Mm-hmm. Good question. For half of it, it would be the 1 centimeter. And then you do that same again with the 2 centimeter. They'd have two different fields, and you're subtracting them because they're going in opposite directions.
So why do you take it out if it's changing?
It's not changing in the path that you're integrating.
Yeah.
They would just be integrating this part, pause, just another integration, that part. Does that make sense? And then subtract those two. Tell your neighbor. Everybody go to 5. Okay. These are they're closer. This is going against each other. These are helping. Okay. All right. So this is probably the worst scenario. It could be on the AP test. Hopefully it's not, but it's in the realm of possibilities. If it does, set it up and skip it. It's only worth 3 points probably. Okay. So we're out here, not on the axis. Okay. Um, here's our point. Here's our radius vector. Um, so we are looking. Sorry, nope. I'm looking for the current that's perpendicular. Um, so so this is going to give me this magnetic field. This part of the magnetic field is going to get canceled out from a current down here. So all I need is the X component. So with this being theta, do some geometry. This is theta. So I just need this component, so I need cosine. So that's the radius of the ring, A, over hypotenuse. Okay, so here's cosine. Okay. And then, good luck. Oh, just kidding. That's easy. Everything's constant. Okay. We out here like now. Okay, here we go. So you get this shape. Here's what we derived at the center, and it does this. Okay, as you go away from it. All right with that? Okay. This is the magnetic moment thing. This behaves like a permanent magnet, has the same magnetic field pattern. Okay. In, out, down. Your thumb points in the direction of the North Pole. Good with that? So they're repelling each other. I want the South Pole to be here. In, out, B. Nice. Okay, I will do something magical so that you can access the practice problem. Practice. You did? Through through my AP, and you didn't go through Blue Book. Interesting. Did you do anything special?
I think it said that it would like lock down your notebook, but I didn't really test it out if it did or not, so I don't know.
That doesn't answer the question.
That's true because I didn't want